Okay, so I'm gonna talk to you today about, here we go, and here we are, about what we can learn about, the Greenland and the Arctic glacier and ice cap from the GRACE and GRACE follow-on mission. And I think that, coming from, a crisis point of view, and, we are really at the time in which we have a lot of tools, a lot of information we can put together. And so I hope that, I get you excited about what we can get with this satellite. And again, Tom is going to talk about ICESat-2, but it's very important, this monitoring system that we have of the Arctic and of the glacier and also of the land water storage. Okay, so just a few minutes, 1 minute, I'm going to talk a little bit about GRACE. This is GRACE, it was a mission that was launched in 2002, and the concept of time variable gravity really started with the launch of this mission. We have 2 satellites that were on free fall, orbiting around the Earth. We know the position of those 2 satellites at every time, and they are distance a few kilometers apart, and they are like a few hundred kilometers in the atmosphere, a few hundred kilometers apart. And the distance between the 2 satellites was monitored every time using a microwave link. And they can measure these changes in distance with such accuracy that is better than 1 micro per second, which is basically, seen at the size of your hair or of a blood cell. And those satellites are attracted by the mass of the Earth. And so when the first satellite is close, let's say to a mountain, is accelerating, the distance becomes larger. And when the second one that is behind get closer, is accelerating, the distance becomes smaller. And so measuring those changes in distance, we can infer what happened underneath and what is the mass that has caused those changes. Now, we are interested in what is changing. We can get this information every month with GRACE, and now also with GRACE follow-on, which is the follow-on mission. And we can see what it changed from 1 month to the other. So we don't really care about the mountain that was there before and is there now. So if we remove the mean, we get rid of everything is there. We can see what changes from 1 month to the other at a scale of a few hundred kilometers and larger. And if you think what is changing on land is water storage in the river basin, in the ocean is mass distribution in the ocean, and over the ice, we have change of the mass of the glacier. And turns out that actually what we measure in the total change underneath the satellite, turns out we know the atmosphere mass distribution well enough. So we use GCM, ECNWF for remove the 3D structure of the atmosphere. And so whatever is left, lies on the surface of the Earth, on the Earth's, our planet. And GRACE was a 3 to 5 years mission, but it lasted about 15 years. And he passed away in 2018. And fortunately, now we had a GRACE follow-on mission. There is a rerun, and here you see the rocket which was launched, was a SpaceX rocket, was launched, and is a rerun of the GRACE mission. But in addition, we have a laser to measure the distance between the 2 satellites. And so let me just go back, to the science to look a little bit at what we can do. So the idea is that you can think about the satellite as they're weighing, the Earth. So we don't know the abs, it's a little bit like I'm weighing myself and I'm trying to see how much my weight is changing. I don't know what is my weight I started for. So all we have, because we are removing the mean field, so the mean value, is it changes in mass. But we use some tool to extract the signal within specific area. And so here, the plot on the left shows the time series of the mass change of the Greenland ice sheets, monthly changes. The blue line are the monthly changes. The red line is filtered for removing all the seasonal, and sub-seasonal variability. And so you get an idea more of the long term and the interannual. And basically, you see, it makes sense. You have like the mass that, is increasing in winter, is decreasing in summer, is increasing in winter. And during the first part of the mission, so we have this data from 2002, we have a small gap during between the end of the GRACE and GRACE follow-on and the start of the GRACE follow-on mission. But what we have, and this works. And again, this is from remote sensing. And this is at the level of the ice sheet, but because, again, we care about the ice sheet because they're a good problem, but also because they're affecting sea level. And that's, one of the big concern when we look at, the Arctic, but in general for global security, because it's going to affect population, it's going to affect economic. So in the first part, we have changes. They are like more regular. We can see like, and overall, we have a more consistent mass loss. And then starting more recent here, we have more, I would not call it erratic, but we have this behavior slightly changed. We have two, I want to point it out, two record melting summer. One was the summer of 2012. One has been the summer of 2019. About 600 gigaton. And I don't know if everybody's familiar, but a gigaton is, if you want to just put in your eye what it is, that's the mass. Is the equivalent of mass that Los Angeles County uses in one full year to take care of all the need from a water storage point of view, so for building, for different activity. And so here we have the, on average, during this period, the mean loss is 234 gigaton per year. So in those years, we have about 600 gigaton of mass loss. And what this, we find that we have this change, in the mass, this large amount, they are actually consistent with, finding exceptional warm summer, and they're very, exceptional in the last century. And this is consistent with the Greenland blocking effect that has been documented and is, shows to be related to the atmospheric circulation that we are observing, is related to the warming in the Arctic. If we go to Antarctica, and I brought Antarctica, I know we are interested in the Arctic, but I'll go back, later, because it's going to affect the sea level in the Arctic too. We have a much different variability. They have more, there's bigger, jump, mass balance is like Antarctica is much bigger. And again, overall, we have big fluctuation of surface mass balance. We have a bump in 2006, another one around 2018. But overall, the mass is keep decreasing. And if you look at the map underneath, you can see this satellite allow you also to see how the mass loss spread. And so in Greenland, we can see that the mass loss, this is starting from the start of the mission, is spreading to the entire ice sheet and is spreading, toward the north. And this is consistent, and eventually we see all the entire ice sheet losing mass. And this is consistently with, following the warming pattern of the ocean, and, with warm water coming, from the North Atlantic off the coast of Iceland. Okay, I'm going to just show you, and I'm going to move a little bit forward. So we can look at the entire ice sheet, but you can also divide the ice sheet in sub-region. And here we divided the ice sheets in a region. They are based on the character of the precipitation and of the mass loss. And we want to see, can we learn more about, with this about what is the characteristic of the mass loss and what sector are affecting them more. And what we find that most of the mass loss, if you see, come from the northwest and the southeast. Those are area where we have high precipitation and glacier moving faster. In the southwest, we have a lot of land terminating glacier, and most of the signal is coming from melting. Here we don't have a lot of discharge, and what we observe also in more recent here, there is a catching up of the north and the north and the northeast, and now the mass loss is like spreading. And overall, I want to say we have this big melting in the summer of 2012 2019, but we have changing behavior. I want to point out that the north is really overall, even if they're not the driver of the mass loss, this region is starting to as a percentage of the total balance fluxes is showing the biggest changes of the glacier. So another thing that we can do using GRACE is looking at the glacier and ice caps. And so here is for the period. This is extended. This is some work that I did with some and I have to mention, all this work is work that, I've done with a lot of the researcher, the student, and there are a lot of people working on this. We can also use GRACE to the satellite to get an information about the overall mass change of the glacier and ice caps. And so we look at the entire glacier, ice cap outside the ice sheet. I want to point out that Greenland include also the periphery, the number that we are giving the peripheral glacier and ice cap. But in this case, we are talking about, here the map of the world and land ice, glacier and ice caps. And I'm going to spend a moment to talk about this figure. So with the square, I have highlighted what are the regions they are in the Arctic. And we find the 7 regions that are covering about 94% of the total glacier and ice cap area of our planet are outside the main ice sheets, are accounting for about 90% of the total mass loss that come from the glacier and ice cap, and about 65% of this area is covered by glacier and ice caps in the Arctic region. And I circle them with like a red box. Here, the glaciers are actually put in order of contribution to sea level. And this accounts for about 70% of the total mass loss. Here, the time series are a little bit different from before. The red line is, the color line are grays. And then there is like overlapping, you do see is like probably it's a little bit small, but there is like a gray line that is giving us this smooth version that remove the seasonal. But I also plotted the MERA2 surface mass balance change. So we for the glacier ice cap, we can assume that the mass balance is a good proxy for the surface mass balance for the overall mass change. This is true mostly, but we know that there's a component of ice dynamic in the Canadian archipelago, some part in the Russian Arctic, but it's a good representation. So we took the MERA2 surface mass balance, and we calibrated using GRACE. So what it means that those models have an intrinsic bias, and here we're looking at the cumulative mass loss, and we know they do a very good job in representing the interannual variability and the seasonal variability. But when we look at, and so we can use GRACE observation to calibrate them. And, part of this comes from the fact that we don't know what is the reference for the mass loss when the system was in balance. But what we find that, there is a pretty good agreement, which is pretty impressive. And what this tells us that we can use this information to calibrate and, evaluate those models. If we sum all those ice sheets, all the glacier and ice cap in the entire world, and we just put them together, we get a total mass loss of about 273 gigaton per year. I want to just do a little zoom because we're talking about Arctic. So we can also, I show the contribution for the entire Canadian archipelago. We can look at the, again, Baffin Island and Ellesmere Island. And so here are the two time series. As you can see, they behave slightly differently. And so we have in the north, we have more the effect of those, uneven behavior from the summer, the affected more, are more affected what is related to the circulation, so the blocking effect and the circulation changing the Arctic atmospheric circulation. But I just wanted to give you some examples, and then I'm going to leave it open to questions. In this case, is the Russian Arctic, France, Joseph Land, Novaya Zemlya, Severnaya Zemlya. Most of the mass loss is coming from Novaya Zemlya. But again, we can look at those glaciers and again, think about the information, how this can be used also in relation to the ocean, try to connect, how the glacier and the melting glacier can interact with the ocean, how the ocean interact with the glaciers. Okay, the last things I want to talk about is, so one of the impacts, of course, we care about the glacier and a lot about the impact that they have on water resources, especially the land glacier, the glacier and ice cap they have on the environment. In the Arctic is going to be a big impact, interaction with the permafrost, the melting of the ice, interaction with the soil. But there is a big impact of this also on sea level. And so here I put a plot of, those are like basically what we call sea level fingerprint. It's like basically is what is the pattern of sea level that we get associated to the fact that we have the present day mass fluxes, ice melting on land and water storage. And so here, this is basically the mean change during, this is like, I just use this as an example, that comes from the melting in the Greenland ice sheets from Antarctica and from the remaining land water mass, but the mean change, so the trend is really controlled by the glacier and ice caps, as you see. And what we expect, what we find that because we are removing a lot from the surface of the, the ice, the Earth is responding elastically, and so there's an immediate response, and so we're gonna have the Greenland uplift, we have subsidence, we have a decrease of sea level in the near field, so close to where the mass occur, and the sea level is going to rise, far. And basically what this map tells us, and this is the sum of all the effect, tells us basically where the water goes. And we care about this because while at present, this may be not the dominant signal in the regional pattern of sea level, as the ice sheet and glacier keep melting consistently at one location, this is a cumulative effect, and eventually is going to dominate and bypass the effect of the ocean dynamic and the thermal expansion. And so we expect the sea level is going to rise more, for example, in the, differently in the equatorial region. And here on the right, I have a plot that shows you what is the cumulative event for the initial year of the GRACE mission. So it's just building up. And so that's why I just thought I'm going to put Antarctica, because what happened in Antarctica is going to really affect in terms of sea level also the Arctic. And just concluding, I think that we have GRACE and GRACE follow-on, and in general, the use of time variable gravity provide, a very important tool to be consistently observing accurate how the ice mass changes in Antarctica, Greenland, and for the glacier and ice caps at the monthly level. We can, we still have a regional mass loss, but we can have a way in which we can try to tease out smaller region. And this we have since 2002 is an important observable for like the climate impact. All glacier and ice cap are losing mass, and the mass loss is increasing. Greenland is losing mass, the mass loss is increasing. We have a change in behavior, but overall it keeps losing mass. Antarctica, the mass loss occur more by sector. So we have the Amundsen Sea sector in West Antarctica is losing mass, Winterland in East Antarctica and the peninsula. And then there's some area they are like increasing the mass loss. And I think that it's important to think about how this data set and, ICESat-2 data and the other observation that we are really important to combine together. And, I just show an example of how we can use GRACE to evaluate and calibrate surface mass balance reconstruction. And again, here is a summary of the contribution during the past, since 2002, so almost 20 years. And we find that, again, 70% of the signal from the glacier and ice cap comes from the Arctic. And I'm done. I'll be happy to answer any question later.
Fantastic. Thanks so much, Isabella. I learned a lot. In the interest of time, I think we're actually just going to move right along and do questions at the end. So our next speaker is Tom Neumann, who is the project scientist for the ICESat-2 mission at Goddard Space Flight Center. So in addition to his job as the ICESat-2 project scientist, his research interests also includes the chemical, physical, and thermodynamic property study of polar snow and ice. He's been involved extensively in fieldwork, both in Greenland and Antarctica. Let's see, he's led 4 expeditions and participated in a handful of others in between the 2 poles. So Tom, you want to take it away? And yeah, he's going to tell us a little bit about the ICESat-2 science data products as they might be of interest to this community. So thanks, Tom.
Cool, thanks, Caitlin. Hey, should I put this thing in slideshow, or is it in slideshow already?
If you could put it in slideshow mode, that would be great.
Boop. How's that?
Perfect. Thank you.
Yeah, it's sort of funny because now of course you can't see anything. I just see the slides, but that's fine. Thanks for the introduction, Caitlin. The material you'll see today, a lot of it is the handiwork of Ben Smith, who is our ICESat-2 land ice data product lead. I also want to acknowledge that. Current status, ICESat-2 has been up for the number of days you see there. the exciting milestone we passed recently was the number of laser shots. ICESat-2's laser aboard the Atlas instrument fires 10,000 times a second, and we recently crossed 1 trillion laser pulses, which is a staggeringly large number and a whole lot of zeros after a 1. A few other metrics or fast facts about ICESat-2 over here on the right. And I'm always pleased to say that the performance metrics for the spacecraft as well as the instrument remain nominal, and everything's good up in space. For folks who are new to ICESat-2, it is a laser altimeter. It generates a single pulse of green laser light that's split on board as it leaves the spacecraft and generates the pattern you see on this figure. The 6 beams of ICESat-2 are arranged in pairs. 2 of them are close to nadir, and then the other 2 are spaced left and right by about 3.3 kilometers with respect to the direction of flight travel. Footprint size on ICESat-2 is small. It's about 11 meters. We've evaluated that a few different ways on orbit, and happy to talk about that. And as I mentioned, the 10,000 shots a second from the laser generates a footprint on the ground in clear sky conditions about every 70 centimeters along track. So the footprints overlap quite a lot from the nth shot to the nth plus 1 shot. Really detailed data in the along track direction, but pretty sparse in their cross track direction. And we'll see a few examples. The next few slides are about data products. If you're already familiar with the data products, feel free to check your email for a couple slides. But if you're not, the data product that's kind of the foundation of all of the other higher level products for ICESat-2. We call it ATL-03, and that's a geolocated photon product. So for each laser pulse that gets sent out, Atlas detects somewhere between 1 and 10 returning photons that bounced off of the surface of the Earth and came back to the spacecraft. And this data product provides a latitude, a longitude, and an elevation for every photon. So it is the big one, aka the big one. A handful of other parameters at the photon rate means that this is a giant product. The advantages are that every photon is there in every parameter, and this is as detailed a look as you can get at the surface of the Earth in the along track direction. But the disadvantages are the same as the advantages. Every photon is there from in the data product, so it's gigantic. Here's a couple suggestions of when you might want to use it. It's kind of cool to look at. We've been doing what we call Photon Friday social media events on Twitter intermittently these days, kind of once a month or so, but some classic scene on the Earth as seen by ICESat-2. Couple of examples of what it looks like in the Arctic. Over here on the left, at least left for me, West Central Greenland melt ponds. This is an ICESat-2 pass from August 2019. You can see that speckle and that wide band of black dots. Each one of those are a photon measured and detected by ICESat-2, and that wide band is mostly due to sunlight. Our laser transmits energy at 532 nanometers, the green part of the spectrum. The sun does as well. However, your eye is hopefully drawn to the large, thick black curve across the middle of that band, and that's the surface. And that surface, if you zoom in, is composed of thousands or millions of individual returning photons that came from the transmitted laser pulse, bounced off the surface of the ice sheet, back to the spacecraft. A couple cool things in here. Yes, you get a good look at the topography. You can see some crevasses in there, but you also see these flat areas where the hollows on the ice sheet in that area are filled with water. So we're getting reflections both off the top of lakes or ponds on the Greenland ice sheet, as well as some of that green light goes down through the water, bounces off the bed of the ice sheet and back to you again. So you can actually measure the bathymetry from space of melt ponds. Over on the right's a little closer look at what this looks like, what ATL-03 looks like in rugged terrain. You can really resolve a lot of pretty small features. You see the x-axis there in meters, so that whole scene is about 1.5 kilometers across, pretty lumpy in that stretch. ATL-03 is pretty unwieldy to deal with, and it doesn't really tell you where the surface is. You have all of these photons, and the challenge is figuring out from those photons specifically where's the surface. And that's where these higher level data products come in. For land ice, the number of that product is 06, ATL-06, and it generates fits It takes photons that are most likely coming from the surface and fits lines to them and tells you what the elevation is and the surface slope is at 40-meter along track posting. So this is a lot smaller than ATL03. Provides error estimates for how the goodness of fit of that line segment to those photons. It's a much lighter weight product than O3, as you see under the advantages. But there are some disadvantages to O6. 40 meters might be too coarse for your science needs, such as crevasses. And 40 meters might be too fine for some of the large scale studies, such as Isabella was showing for changes over the entirety of the Greenland ice sheet. There'll be a lot of little segments that go into that. To do some examples of what this looks like, credit to Nick Holshoe and Tyler, who's here on the call. The little black segments are the ATL06 fits to that kind of fuzzy photon cloud from ATL03. And that's what O6 is trying to do, is to make a best fit surface to that return photon cloud in the O3 product. You can aggregate all of these elevations in O6 to make a map like this for Antarctica, or like this for Greenland. These are elevations measured over the two great ice sheets for the month of April 2019. So it gives you a sense of what our monthly coverage is. Of course, this is, you can always lie with these kind of figures because our footprint size is only 11 meters. And in a month, there are somewhere around 450 tracks globally. So this is still pretty sparse data, even though MATLAB tends to fill in those gaps. O6 does a lot of things really good. It has a hard time in some places, like this example here over a melt pond. Sometimes it's tracking the bottom of the pond. Okay, great. That's the ice-water interface. And at other times, its fitting algorithm is being pulled up to the surface of the pond. It's an ongoing area of work with O6 to try to improve how it handles these situations and other rough or complicated terrains on the ice sheets. The next higher level product is ATL11. ATL11 is aggregating a whole bunch of O6s and correcting for both along and across track slopes. It's like ATL06, but it's easier. Aggregating data over a particular cycle of data. The ICESat-2 cycle is 91 days, and that contains 1,387 revolutions around the Earth. So ATL11 is aggregating those for a particular cycle. And that's an advantage, right? It's bringing together multiple repeats of O6 and grouping them together, and it makes it easy to do elevation change between, say, cycle 5 and cycle 3, or cycle 2 and cycle 1. It is a much smaller and easier to use product than O6, but you do lose some detail relative to ATL06. There's fewer parameters there. And it still doesn't work very well over really complex surfaces like really rough outlet glaciers. Some examples of what that looks like would be here. Another Tyler special. Thanks, Tyler. Up on top is the elevation from two different cycles plotted right on top of each other, or perhaps three cycles plotted on top of each other, and they hard to see the differences. Down in the lower panel, we actually calculate what those height differences are relative to cycle 3. So you could see perhaps it's cycle 4 in the red and cycle 5 in the magenta. So you can actually look at that height change over seasonal timescales, over 91 days. And in this case, what you're seeing is this track would go from grounded ice on the left over to floating ice on the right, and where that elevation change decorrelates, that's primarily due to the different tide state at the time the measurements were taken, as well as any roughness or advection of roughness that complicates those kind of elevation change measurements. You can make cool maps like this by differencing the different cycles in each ATL11 product. I'll just start on the left. I won't go through all of these, but the one on the left is kind of cool. It is cycle 4, which is quarter 3 of 2019. So that's fall 2019. I'm sorry, that's cycle. I mismatched the cycles and the dates I see down in the bottom. Suffice to say, you can do this seasonally, and you can watch the ice sheet collect collect snow in the winter and the height goes up, and you can watch it melt in the summer, and the height goes back down again, and you get a sense of the magnitudes here with the color bars. One of the cool things you can do, and people are just starting to scratch the surface on, is looking at short timescale changes in the surface height, which mostly tells you about the surface mass balance. By doing these differences, you can watch it snow, you can watch it melt in Greenland or around surrounding ice caps, which is cool. The next simplest products are ATL 14 and 15. That's the gridded elevation and elevation change over the entire ice sheets. The advantages is that bringing together repeat measurements from many different tracks and many different cycles to map the surface height and then surface height change. The disadvantage of this product is it isn't out yet, but it should be out by the end of the calendar year. That's at least a goal I put for Ben and his team, who are working on it, and we're pretty close to that. A preview of what those are going to look like is here in these figures. On the left is Greenland height change from 2019 to 2021. Color bar is as you see there. Not surprisingly, Greenland lost volume all around the edges of the ice sheet. By either using a firn model or making an assumption about what the density of the material that was lost, whether it's snow, ice, or somewhere in between, you can convert that to mass and compare it with the GRACE time series that Isabella was showing in the last presentation. In addition, these products provide an height change uncertainty estimate that you see in the center panel. ICESat-2's individual elevations are good to about 30 centimeters. Each of those photons that you get in ATL03 are good to about 30 centimeters. So aggregating millions of them together, you are able to reduce your errors quite a lot to get down to pretty small numbers for height change. I'm going to go on to the next one. Yeah, how good are the data? We're often asked that, and the way we assess it with ICESat-2, or two of the main ways we assess it with ICESat-2. On the left is a map of Antarctica where we've done a ground traverse led by Kelly Brunt. We've done 3 of them now, where we go out and survey the elevation of the ice sheet with high precision GPS and just compare ICESat-2 data against GPS data over and over and over again. And you see some of the metrics there from one of Kelly's recent papers on assessing ICESat-2. The other way we do it is with corner cubes. That middle figure looks like a plastic cap with a little hole in the middle, but in the middle of that, there's actually a little piece of glass, a corner cube retroreflector that's sized to return green laser light really efficiently. By surveying the locations of those stakes, that one happens to be in Antarctica, but we also have them in other places that aren't on ice sheets. You can make figures like the right, a long track distance on the x-axis, height on the y-axis, and the corner cube returns pop right out at you. You get the ground return down below at about 1167.5 meters, and the corner cube is about 2 meters higher than that. So that allows us to assess not only the elevation, but also our geolocation. How well are we providing the latitude and longitude associated with those corner cube returns? And so you can see some of the metrics there. The corner cube work is primarily led by Lori Magruder from University of Texas. Incidentally, that's also how we often assess the footprint diameter on orbit. And that's where that number of 11 meters or 11.3 meters comes from. Bottom line on the data products is that the height accuracy is currently better than 10 centimeters, but it really depends on your particular terrain. Middle of the ice sheet, it's better than that, but if you're on Jakobshavn and it's all broken up, or you're looking at the Melange in front of Helheim, it's going to be worse than that. The horizontal geolocation accuracy you see there is better than 5 meters. It also kind of depends on where you're looking. It can be a little better, a little worse than that. And the other one I'd mention is the last one. In the polar areas, such as over Greenland, ICESat-2 tries to illuminate the same patch of ice every time, or the same geographic coordinates. So on each pass of a given track 617, ICESat-2 is aiming to hit those same latitude and longitude. The footprint diameter, again, is about 11 meters, and our pointing control for that repeat ground track pointing is about 10 meters. So you really can compare cycle 3 with cycle 4, or cycle 4 with cycle 5, because it's illuminating the same, plus or minus 10 meters, spot on the ice sheet, which is phenomenal. The point and control of this thing is really amazing. Our data products all go out through the NSIDC DAC, which I know many of you are familiar with. So far, we've had just over 18 million files downloaded by 4,000 some registered users. ATL 03, 06, and 11 are out there right now, and you should feel free to go grab them. 14 and 15 are coming soon in the next couple of months. You don't have to start from scratch. It's not like you'll download one of these and say, okay, let's see, line 1, open this file. There's a lot of tools there to help you get started. And they're linked through the NSIDC landing page under Tools and Services. I've highlighted a few of them to be aware of. The Hack Weeks are great. Tyler and others and Ben put together tutorials on how to find the data you want, how to download it, how to plot it, how to work with it. And I've heard from at least one other person on this call, Bob Hawley, that found a really useful way to get started. You didn't have to attend the Hack Weeks. They're all that material is available online. So yeah, don't be intimidated if you've never worked with it before. We're trying to make it as user-friendly as we can. And yeah, that's about my time. A couple of links up there in the upper right. I'm happy to take questions if there's time. Thanks very much.
Awesome, thanks, Tom. There's plenty of time for questions for our speakers. Is any? Oh, Bob's just clapping. Okay. So it's Trevor. I guess, Tom, I have a question for you. So ATL 15 is going to be that gridded ice sheet height product from ICESat-2, whereas ATL 14 is going to be that reference surface that ATL 15 kind of uses. So how do you anticipate the science community using ATL 14? Or is the project just kind of assuming that ATL 15 is going to be the product that more people use?
Yeah, 14 will be handy if people want to compare this reference ice sheet surface, like you say. It's going to be at a particular epoch. Tyler might be able to remind me what epoch the ATL 14 reference surface is relative to. I thought it was some point in 2019, but honestly, I forget. It'd be a great thing to compare against RIMA or Arctic DEM, which are compiled from lots of data over a much longer time span. And that, you're right, that height change from ATL 15 is certainly going to be used most commonly, but the two of them together allows you to take reference surface plus height change if you choose to get back to absolute height space. Tyler, any comment on the, I don't know if Tyler's still here, on the epoch of ATL 14?
Yeah, that's a good question, Caitlin, on the science applications of ATL 14. We're not really expecting it to have as wide of reach as RIMA, because RIMA has such high resolution in terms of spatial, but it does give a pretty accurate baseline at its specific middle epoch. And I think it is in 2019, but I'd have to double check on the exact one. But it is fairly early in the mission once we started getting good pointing control. So I think it's either cycle 3 or cycle 4, but it's sometime in 2019.
Okay, cool, thanks. Isabella, you got your hand up.
I actually want to, it's like I'm going to do a little bit but I thought like Tom did such a great job in talking about product, and I want to say those and I kind of talk about what you can do with GRACE, what you can get and not. So those time series are available. We have repository for the sub-region and also for the glacier and ice caps. They're like data available from the big, the website. And I think that also something that is very important, and I think becoming more and more, is like, how do we, what is the user want? People that are doing the research. And so let us know what are the things, anything should be, and let's work together to provide this product in a format. There's a format that is most useful and how can be used for, even people that are not necessarily focused on the ice sheets, on the glacier, but what is the impact they want to combine it with other data set, and how do we provide errors and uncertainty. And so just please email and help us figure out that. but all those product time series are available, and you can just download it, and we're welcome to provide. There's like a good group of people that have this.
Yeah, Simon.
Yeah, I mean, so building off Isabella's comment there, I mean, these are pretty technical data sets. Do you have examples where you have worked with, sort of researchers on the ground that don't have the NASA background, the stamp of approval of a science team, a project member, to use the data sets? I'm getting at the issue here that this is an interagency presentation, and I mean the data is just absolutely fantastic. But how do you put this in the hands of just regular researchers who don't have that background in these data? Just are other examples where that's worked?
And maybe I can just take. I mean, it's like I know that ICESat is doing a great work in trying to creating, we call a level 3 product, which are like product they're off. I think it's a product. I think that we have example of people that have been using it. We're learning from the user in terms of what are the product they're gonna need, and it's a very. I mean, I'm spending a lot of time also these days to think about, both we do work also some work on the water storage and hydrology. How do we provide this to stakeholder and what? So it's a lot of take and interaction. That's why I'm saying, so yes, we can give time series, we can provide errors, we interact, we're trying to, when we, release the data, provide also some way in which, if you have a big footprint, how do we compare and provide some codes also. But a lot of time, you're right, the codes, is too complicated. So people want, I'm learning the shapefile are the great thing these days, no NetCDF, that's like forget it. And so I do think we do have example of using them. I think that there is a long path still. And so that's why I say that we need to work with the user, especially for other community. I think that this is a great opportunity, this interagency effort. And how do we package them, and also what variable and what component people want. And so it's just like try to figure out this better. But this said, there are time series, they're like maps, grid and map that can be imported in a GIS software. We try to use I would say open source, probably trying to create block, they're self-explanatory. But I do think that Simon, that's a very good point. I think that we are working. So bug us and let us know how do we do better, because there's a lot of interaction and looping back, and that's a big part of we want those products to be used. We just don't do it for this. So.
Yeah, and on the ICESat-2 side, we have our applied sciences group that works to close exactly that gap, Simon. One example might be the Arctic shipping and people doing Arctic shipping, that our freeboard measurements from ICESat-2 realize this is a land ice crowd, but a sea ice application. But yeah, they're interested in as close to near real time sea ice freeboard and sea ice thickness estimates as we can provide. And in the next couple of months, we're going live with our what we call low latency data, which is about 3 days old or so, but it'll help with things like that. To do more terrestrially, we also work with a lot of people from the U.S. Forest Service who are interested in these kind of data. And we do try to make it as easy as we can, put data into the formats that they want, where it's feasible to, so that it's easy for them to use these data along with products that they're already familiar with, like say Landsat or something like that.
Great, thanks.
Yeah, great question and great answers. Thanks both. Mike, you've got your hand up.
Yeah, hi, can you hear me?
Yep.
Fabulous. Thanks to both of you for the presentations. Those are great. I have a question about ICESat. I know that in Alaska, there's a challenge with utilizing ICESat-2 for glacier change because it's not designed to do the frequent repeat schedule. And I'm wondering if, as these gridded products come out, if there's any intention to deal with that in some way. Is there a strategy for gridding glacier change in Alaska, or is Alaska gonna be omitted from those upcoming releases?
Yeah, the two releases I mentioned, ATL 14 and 15, are really focused on the big ice sheets. However, we don't want to neglect our mountain glacier colleagues that are working in high mountain Asia or Alaska. So what we've been doing is that a few times a year, sort of twice a year, where we'll end up doing repeat pointing everywhere, so that, provided that it was reasonably clear over Southeast Alaska, which I'm told happens sometimes, you would end up with repeated data that's coincident geographically, so you can do height change. With our orbit and our beam pattern and footprint sizes, it's still sparse sampling, right? Unless you're a really, really big glacier. Well, if you're a big glacier, I'd wonder how you dialed into this. But if you were studying really small glaciers, it's going to be hit or miss as to whether ICESat-2 data gets it. I kind of think of ICESat-2 data as sort of pencil lines across your map or across the landscape. And if we happen to be in the right place, or along the strike of the valley, or whatever is most interesting to you, then great. But I'm totally aware there's lots of places that ICESat-2 just doesn't help very much because it's too sparse. I don't know if that answered your question very well.
Yeah, it did. Thank you very much.
Kathleen, maybe can I add something following up of like the use of the data? I think that there is a part of how do we make people is also try to, I don't know if cultivate is the right way, but create some educational material, a way to reach out to undergrad, graduate student, also community. So how do we connect with the stakeholder, also the level of make them aware of what are like the the need that they have, and how we can and explain it, and just do have this feedback. And I would say, I think we start working with social scientists. They're going to help us to reach out to those people, and that's part of I've been to how do we get feedback, and how we fit this in to just improve this, make this science more usable at the level. Caitlin, you mentioned there was this knowledge to the land, and of the community, and how this is impacting. We really want to make sure that people can use to make decisions this data.
Yeah, and kind of to piggyback off of that, so I work at NASA headquarters, and more our management is kind of pushing us to use more, to deal with the applications teams and get more out into the community with kind of marketing these missions as things that everybody can use, not just NASA scientists or PhDs. Any other questions or comments for our speakers today? All right, doesn't look like it. Well, thanks everyone so much for joining us this afternoon. I don't think we have another Glaciers and Sea Level collaboration team meeting on the calendar set for this year, but look to hear more from us in the next calendar year. Hopefully by then we'll have a new Arctic research plan that we're working towards, and we'll have some new and exciting events planned around that. Anyone else from an IARPIC collaboration team here want to make any announcements? All right, I guess not. Meredith, anything else to close us out today?
Just to say that if there are general announcements from the community, so any papers that have come out, or events that are happening, any AGU talks you want to plug, now might be a good moment.
Tom or Isabella, any exciting GRACE or GRACE follow-on or ICESat-2 events happening at AGU this year?
Yeah, we're going to have a couple of town halls, right? Today we've mostly talked about polar, but it turns out ICESat-2 as well as GRACE takes data globally. And so if you're interested in what we're finding over trees and oceans and cities and lakes and whatever else, come on out to one of our town halls. We have one on the Monday of AGU. That's our sort of general mission town hall, and there'll be a second one that's specifically on applied sciences, so how people are using ICESat-2 data in a decision-making context, and that's Wednesday evening of AGU week.
And yeah, there's going to be a lot of session and some, is the town already to Grace. I also would say that get in touch with people, and because I do think there is a lot, as Caitlin was saying, NASA is really putting a lot of emphasis in being able to apply, and I think I found that is actually very motivating both for us and for researcher, because it really makes us, we love to solve problems, but how do we use this science, and now we just do things that like really, especially now. And so I do think there is a lot, and I'm happy to send if they're like, I don't know if there is a mailing list, but if there are some event or some places where there are some, forum to talk about this, I'm happy to share it, if people are interested in.
Yeah, sure, Isabel, if you want to send it to me, I can post it on our collaboration team page on the IARPIC website.
Sounds good.
Great. All right, well, thank you to our speakers, Tom and Isabella, for joining us today and educating us about these awesome missions. And we will talk to you all again soon. Thanks, everyone.
Thanks, everybody.
Thank you.
Thanks.